man. Always stood on my own too. I was used to not having shit. Now I do whatever I want to do. Still down with my same niggas. And I don't be
This is about summing an infinite series. So summing in the sense that we're adding things. Okay, so we can, first of all, let's say we can represent, so this is an important part, we can represent an infinite series as a partial sums. Okay, so this is a pretty useful statement. So this basically means that we have some s sub n. So this is what represents partial sums. Okay, this partial sums is technically a finite. So finite just means it ends somewhere, whereas infinite means it doesn't end. It has no bounds. So this is a finite series, or finite sum of terms up to, and this is an important part, including the nth term. So in this case, the formal, I guess, equation would be partial sums equals this, little n equals 1, up to big N, because this is the same big N, all right, of the sequence an. This is our general term. This is going to equal a1, because we're starting at n equals 1, plus a2, plus a3, all the way up to until we get to a sub big N, okay? So for example, just a little example down here to illustrate. Let's say we're given the sequence an equals 1 over 3 to the n, okay? And we're asked to find, I don't know, S4. So S4. So this is the partial sums up to the fourth term. So that would just be A1 plus A2 plus A3 plus A4, okay? And then this would be 1 over 3 to the 1, plus 1 over 3 to the 2, that'd be 9, plus 1 over 3 to the 3, 27, plus 1 over 3 to the 4th, which is 81. Okay, so this is what the partial sums up to the fourth term would look like for our given sequence. All right. Now, so this, if you're wondering, this following thing is called an infinite series. And we can tell because of this giveaway, because it goes to infinity, right? So, basically, this might or might not be a theorem. I know it's stated in your textbook. So this infinite series converges to a sum s, if its partial sums, so s sub n, right? If its partial sums converge to s. And I'll explain why. So this is how you write it mathematically. So limit as n goes to infinity. Well, wait, we have a big N here of the partial sums equals limit as big N goes to infinity of, you can start anywhere at a certain number and then go up to infinity. It's not going to matter in the long run where you start, really, of the sequence equals s, which is then, so this is kind of like saying that, remember when we did limit of functions and the upper bound for our integral was infinity or something, then we would have to use, I believe we used the letter r to replace it, so then we said r goes to infinity, and we had to take the limit. So this is basically saying that the limit of this is going to be the partial sums, and then we're just going to take the, remember in the last slide we did S4, S sub 4, so that was the partial sums up to the fourth term. So now what this means is we're just taking the partial sums, so this is like partial sums, up to the, okay, this is going to be very grammatically wrong, but up to the infinity term, something like that, up to infinity term. Yeah, so we're just taking up to as many terms as we can possibly calculate, kind of thing. Okay, so again, we have the two options. If limit, well, this is the first option, obviously. So the limit's going to exist, and both are going to converge to the sum s. But if the limit does not exist, then we say that the infinite series, so infinite series, and diverges, right? And then we have the more specific case of if limit is infinite, the infinite series diverges, and this time to infinity, as we would expect it to, basically. Okay, and then the next thing, I'd just like to note, as your book also tells you, to remember that there is a difference between, I should have abbreviated that. So there's a difference between an and this. This is the, okay, so there's a difference between these two, even though they might look similar because they both have the an in them, but this denotes a sequence, and this is an infinite series, and they are different. So even if you have the same an, these values might be different. Okay, you can't just assume that they're equal right away. Okay, so the next thing I'd like to go over is the geometric series. So geometric series. So this is when we have, remember this is the general term of CR to the n. So now we're doing an infinite series. So this is going to be n equals 1 or 0 or wherever you want to start, up to infinity of this an, which is now CR to the n. So this is the same thing as, so let's say you were to start at 0, so then we'd get CR to the 0. So R to the 0 is just 1, so we'd get C for the first term, or to the nth term, which is 0 in this case. And then we're going to go up by 1, so then we have C times R, then we have CR squared, and then we have CR cubed, right? Because then the C just stays a constant. And then all the way up to infinity, basically. Okay. And then we have, let's see, so what is our partial sums? So what is Sn? Because that's what we're concerned with now, is the relation between the infinite series and the partial sums. So the partial sums would be, and this is the definition of partial sums, is n starts at some value and then goes up to capital N, right? And then we have our CRn here. So this would be kind of like C plus CR plus CR2 plus, and then all the way up to until we get to CR to the capital N, right? So if our partial sums were 4, then we just go up to C times R to the 4th, okay? Also, so this is kind of like our first equation, because this doesn't really tell us much. I mean, it would be very tedious to, let's say your capital N were something like 10. I don't think you'd want to calculate every single term. So what I'm going to do now is find a more concise formula for what our partial sums is. So here's our first equation, and then what I'd like to do for the second equation is multiply the left and the right by R. Okay, so R times partial sums is going to be equal to, and then I'll write it a little bit over here so I can kind of line it up. So R times Sn would be, if we're multiplying everything here times an R, then we get CR for our first term, CR plus, and I'm just lining them up for convenience, CR squared plus CR cubed plus dot dot dot. And our last term would actually be this thing, so C plus C times R to the N plus, sorry, I don't know why I put a dot, to the C times R to the N plus 1, okay? So from here, what we can actually do is combine these two equations, okay? So now, at this point, I'm just kind of doing a proof, which is also in your book, but I thought it might be nice for you guys to see it, like, written out. So now I'm going to subtract the first equation minus the second equation, okay? So in this case, I don't know if you guys have seen, like, well, it's kind of like a system of equations thing, and we're just going to solve for S sub n. So on the left, we get Sn, so Sn minus R S sub n. And then on the right side, when we do the top minus the bottom, so ignore this part, that was just for calculation purposes. So C minus, there's no other constant, so we're still going to get C. And then we have CR minus CR, so these ones cancel. These ones cancel. So all the middle terms are going to cancel. And we also have, there's still, okay, you can kind of, even though I didn't write it, in the dot dot dots here, you still have a CR to the N. That one comes right before this one, actually. Okay. So these would cancel as well, but then we would get, then you have like a 0 minus this last term here. So the C in the front and the minus C to the R N plus 1, those are the only terms that kind of like survive in the calculations. So then here on the left, I'm just going to simplify. So we're solving for S sub n. So if I'm going to factor that out, I get 1 minus R here equals C. I'm going to factor the C out. 1 minus R to the N plus 1. Okay? And then finally, this is what we're going to get for our partial sums formula, is C times 1 minus R to the N plus 1 over 1 minus R, right? Okay, so then building off that, so this is really important, and I'm going to border it in squiggly lines because that was a fun proof. Okay, so on the next slide you'll see some more formulas derived from this thing that I just calculated. Okay,